Uh, there's interesting case that we can use with a simplified equation, and such kind of analysis will also appear in some cases. That is, if the project life is very long, and or sufficiently long, because it's long enough, it's equivalent, or the result is very similar to infinite. So suppose we have a number of equal payment which is infinitely long. Okay, so how can we calculate its present worth? But fortunately, if you take the equation that we used earlier, given a find p, or this given a find p, which is a conversion from a to p. If you use the formula that or that equation that we have, in fact, you can see that when n equals infinity, then the equation can be simplified into a over I. Okay, so we just need to take all a divided by I, then we can get the present value of them. Okay, so remember that this is a special case. So what if we have this kind of series? We have from year 1 to year 10, we have 1,000 returned. From year 11 to the infinity, every year we have 2,000 in return. And when we are considering 10% MARR, what will be the present value? What will be the present value of these cash flow? So, based on what we have just seen, in fact, we can consider. Now, there are different ways to compute that, but basically we can consider that we can divide it into two parts. One part is 1,000. The other part is another 1,000, but from the 11th year. So what happens is we take this 10,000, this 1,000 to infinity. We can easily compute 1,000 over 10%, right? Right from the beginning to infinity. How about for this additional 1,000? In fact, we can think of we are right here. So if we look at this from this point on, it is still 1,000 to the infinity. So we still get 1,000 over 10%. But the value that we get will be the value at this point, the end of the 10th year. Then we need to take it from that point to the present time. So it is a given f find p 10% for 10 years. So the result is 13,855. Okay, so you dramatically simplify the way that we compute the result. We can look at one example, which is a practical example, like investing in some facilities, and that facilities will be able to generate some income for us. Okay, so these are the relevant numbers. Let's just look at the cash flow diagrams. So this person has been saving money over the past 9-10 years, and then this person decided to invest on a hydro project, and from then on there will be 120,000 return every year for 50 years. So again, I guess we can all compute this, right? We take all these value and compute, bring it to right now, so that we know the value of it. And we take all these value, given A, find P, we can get a value. And we want to see whether or not the inflows, the net inflows minus the net outflows, whether or not it's greater than 0. So we do the conversion, as I said. We took every cash flow and bring them all to the future because they happened in the past. And for those return, we bring them to the present. That is the end of the previous saving. And we are looking at 8% return, and for 50 years. So we can compute its present value. And this is return, this is investment. So you subtract them and you get B2 minus BV1 and get 367K, which is greater than 0. So it is a good investment because its net present value is greater than 0. Okay. What if the project life is infinitely long? What if that happened? Meaning that your investment will still be the same, but your duration of the return cash flow is infinite and long enough. Okay, so we know already what we need to do is just take this A divided by the interest rate 8%, then we'll get the present value. And then again, this is investment, this return minus cost, and again we get this positive number. But since we have infinite period for the return, chances are the return will be higher, but not much higher. But previously, the analysis showed that we will accept the project. So chances are when we have infinite project life, the result will be accepting the project too. So we can look at another example which is very similar to the previous one. Basically, we have construction costs, we have annual maintenance costs, and we also have renovation costs every 15 years. Okay, and our planning horizon again is infinite period. Our interest rate is 5%. So we are trying to see what will be the total cost at the present. Okay, so we can look at the cash flow diagram. It's the initial construction cost, and the operation cost is 50,000 per year. But every 15 years, we have an additional 500,000 maintenance cost. So what will be the total investment and operation and maintenance cost? So again, this is something that we can deal with. Although it seems to be quite complicated, we have so many cash flow that we need to compute. It's infinitely many, and we have different periods. But if you think of it logically, I think you will also figure out a way to deal with them. First of all, this 50,000 equal payment infinitely long, we know how to deal with it, right? We take this, all these, divided by its interest rate. Just one of it, I mean, divided by interest rate, you can get its present value, right? But the renovation, or these are maintenance, these are renovation. Okay, these are renovation. Is 15 years apart. They are of the same value, 15 years apart. So how can we get its present value? How can we get its present value? So one possible way to think of it is we try to bring this value to the present time. Every one of them will bring it to the present time. Okay, every one of it will bring it to the present time. In fact, what we can do is we can still convert each of them into 15 equal payment. They will be identical. So what we'll do is we take this future value given f, find a, we can compute its equal payment, and they should be the same all the way to infinity, right? So we take this and compute 15 equal payment. Then we can have another series of this kind of data, which will be that value divided by 5%, and we can get its present worth, present value. Then we add this and these together. That will give us the total worth. So this is what I just described. For the initial investment, initial construction is that amount. Maintenance cost, it happens every year for infinite number of years. So it's 50,000 divided by 5%. And renovation costs happen every 15 years. And as time goes, it gets bigger and bigger. But then we can take every one of these renovation costs and compute given f, find a. So we break it down to 15 equal payment, and all through the life cycle, lifespan to the infinity. So we can get this, right? Given f, find a, then is 500,000. Also, just as I said, there are many ways to compute, to compare, and as long as you understand the essence of the time value of money, as long as you can convert them into a form that you can manage, then you can process the cash flow efficiently. So previously we said that we can break this 500,000 into 15 equal payment. So we have an infinite series of annual payment, right? However, we can do it in a different way. You just imagine that this is the point where the renovation occurs, and we just need to look at the interest rate. The interest happened in this period, and it will still go to infinity, right? So rather than break the cash flow down to 15 equal payment, we can compute a new interest rate, allowing them to accumulate based on the interest rate or discount based on the interest rate. So here we have 5% for each year. For 15 years, we know this equation already. We'll get almost 108%. Okay, 108%. That is the interest rate that we should use to deal with this cash flow. So we use 500,000 divided by 1.07 is more than, again, it's more than 100%, and we get 463 point something, 463,000. Right? If you look at earlier data, you know that they are the same. Okay, so different ways of computation, and it will give you the same results.